Hello and welcome physically and virtually to our conference. Now let me see how to deal with all this. Here we are. Okay. Sense disambiguation in large image collections. Is it possible? This is joint work with two young ladies, Olga Krinicheva and later Evelina Nikolova. We started it 4 years ago, with the intention to check, is it possible to disambiguate the tags in very large repositories of images that appear nowadays? And we consider this as one example to understand the meaning of the image. One example from language side, looking at the tags to understand what is the meaning of the image. What is image tag in general? These are keywords, meta-annotation. It is assigned to an image to facilitate its citation and retrieval from digital collections. You know, these tags appear to all digital objects, to all content pieces, and this became popular and important in the recent, say, 15 years with the so-called Web 2.0, when the user-generated content appeared, and it is prevailing today. We all upload images in social sites. In order to share them, we all insert tags because we want to express the meaning of these images when we upload them. And this is how the field of the focus on the use appeared, and we want this use to be easy, our images to be found, to make retrieval by searching with keywords. And this is how all this became very popular, and it is now our practice, and everybody uses images and their tags. What is semantic gap in automatic image analysis? In general, in computer science, when you use semantic gap as a term, this could be defined as difference in the meaning between construct form within different representation systems. What we have in image tagging, on the one hand, the computational representation at low level for the computer, the image is a set of pixels, and the computer knows the coordinates of these pictures and what stays in every picture. On the other hand, the users, the human, imagine that we want to address these images in natural language, searching in queries in Google. We want to address the tags which are words in natural language. And this is how we have this semantic gap between the low-level representation, and because we are human, we think that our representation is high-level. So we are the high level, the computer uses the low-level representation. So we have two representation systems and the semantic gap between them. How tags appear in these large websites? Are they important? Basically, tags are assigned in two ways. Manually, when the authors upload their content, their photos in social sites, or automatically by software tools auto-tagging systems, and we'll see in 1-2 minutes a demonstration online how the computers auto-tag images, and this is a process which becomes very good, better and better every day. Usually, tags are assigned not as isolated words or phrases. They are a kind of abstracts, and in the typical case, we have multiple tags for each image. We put multiple tags in order to convey the meaning. And in this way, from this perspective, the tag size disambiguation is a task very similar to word size disambiguation when we search for annotated digital objects in the internet. Simply, we don't search in text, we search in images. What is important about disambiguation? If we disambiguate the tags in the large collections we have, we can translate these tags in other languages. This is appealing. Also, another important issue is that if we disambiguate the tags, we can aggregate objects in the social sites which are tagged with the same keywords. So by itself, this is one important task. Concerning the manual notation, we can say that it is subjective, very often emotional, and refers to the purpose of the user who uploads content in social sites. For instance, sweet might tag the word sweet, the tag sweet might tag a collection of pastries. This is a Balkanic picture with typical sweets in the Balkans. We can say that kids and babies are sweet, chickens are sweet, but here the intention and the purpose to use this tag is different. It is again subjective, emotional, and so on. When I talk about tag disambiguation, we worked only with content-based tags, because the emotional one, it seems undecidable to me to decide what is the meaning of these tags. But when we have content-based tagging, it is ambiguous too, because the words we use or the taggers use are ambiguous. Here we have crane, this is the animal, and also the machinery. And when people write crane, for instance, photographs who upload their photos in different sites, they don't think about the ambiguity, they simply tag the image and upload it. And now we'll have a short demo of automatic image tagging. To see the issue, we'll go to the site of Imaga, which assigns words to images with their auto-tagging platform. Imaga is a Bulgarian company specialized in image analysis, and their tagger, their image classifier, is trained with lists of senses from WordNet, and this tagger associates shapes and patterns of pixels to pieces of the image that is given to the tagger. We'll see it in a minute. And actually, auto-tagging is a difficult problem. It requires extensive training. And especially in the case of Imaga, after assigning core tags with probability of correctness of recognition, the auto-tagging platform borrows tags from similar images which are found in other very large image repositories, and ambiguity appears within these additional tags. And the platform, you will see this, is very good in automatic recognition of content when it goes about the object and the patterns that are displayed in the image. Let me go to the demo and show you what we prepared. Here is the, let's start from the beginning. So you see that we do it online, really not So this is the tagger at the site of Imaga. Добре. Да го направим заедно. Нека вземем един имидж от авторите. Just a moment to ensure that everybody sees the demonstration. This is the tagger, and let us try to analyze this image. We go to the tagger and upload it in this window. And the system tells us this is surgeon with 100% probability, doctor 68%, medical, medicine, hospital, health professional. You see the probability of relevance, the relevance decreases. Professional, nurse, clinics. Now the additional tags, they come from somewhere else. And we have here man, people, uniform, patient, person, mask. This is important and very actual for today. And then we go down, and it continues. 50, 60 tags. Let us stop at code, relevance 20%. How to translate? The system can translate these tags, say in Bulgarian, chirurg, lekar, medicine. These are the core tags. Let us go to code. Code is translated as palto, but could be translated as хирургическа престилка. Simply the system is not able to do disambiguation and cannot choose the proper translation in Bulgarian, especially for these tags. Let us make another demo. You will see how well is trained the system. Bicycles. Verify. Try again. So this is statue, 100%. Monument, landmark, sculpture, another image, lungs, cartoon, symbol, no. The classifier is not well trained to recognize this anatomic picture, but was very good with landmarks. And we'll need later this image. Again, we have to verify something to show that we are not robots. So tree, forest, river, woody plant, and additional tags, long list of additional tags that are relevant but less relevant to the picture. But as you see, and here we find somewhere breach was 11% or something. Breach 14%. When I prepared here, this is the picture. As you see, the classifier is, to me, one of the best in the world. Other people say too. Probably, sure, Google and Amazon are better the best in image recognition. But you see what we have here. We put an image into a computer system and we receive keywords suggested because these keywords, according to the classifier, characterize the content of the image. And then we have to work, this was our idea, to work with the natural language description in order to disambiguate the tags. We go back now to the slides. And we go to the next slide. What was our approach to this problem? Can we recognize automatically the intended meaning of ambiguous image tags in large professional collections? We used one site called Professional Image Marketplace. Why professional? Because we exclude the manual, emotional, subjective tagging in the social site when you upload private, personal photos. We prefer to work with content-based tagging, and that's why we took this site. If we can recognize automatically the intended meaning, then the information retrieval becomes easier, and certainly the machine translation of tags to other languages. As usual, we rely on list of senses from WordNet in this early work, but now we think about Wikipedia because Wikipedia is a larger resource with many terms appearing every day, translated in many languages. And when we started about 4 years ago, we developed one algorithm for tag sense disambiguation, which is based on the algorithm of Lesk, extended to glosses of the superconcepts, subconcepts, and the sibling concepts in WordNet. And then the evaluation was only manual because we didn't imagine at that first moment how to evaluate our approach. Later, we found another image collection, and I'll talk about this too. And we tried to involve this second data set in a kind of evaluation with word embeddings, so to check whether our initial idea was correct. Let me explain the first idea about taxonomy disambiguation. But first, why this task is difficult? Because tags are assigned by authors for a variety of reasons, or by auto-taggers, and there are errors. Tags are not the names of objects seen in the photo, and they are often ambiguous. You certainly know that integrating vision and language is a principal target and goal in the artificial intelligence. This is one of the basic features to achieve intelligence like the human one, because we have the image and the language, and we somehow use them to complement each other and build some sense, some meaning from the two objects, linking them naturally, which is the goal with the computer. But today, this is still not achievable to extract meaning from videos. People try with videos aligned with descriptions, but the progress is only in small steps. One of the basic difficulty is that it is unclear how different methods generalize beyond the data set they are evaluated on. And also it is unclear how data might be useful for moving the field beyond a single task. What we do now is based on tags only. If we switch to whole sentences or something else which accompanies images, we will not be able to apply the same technology. And okay, let me start with the first example. The algorithm of Lesk and the WordNet glosses. Imagine that you have the image here with the oranges. Okay, oranges, and this is real image. And the tags are 7, orange, fruit, plate, food, tasty, close-up, vitamin. What is orange in this case? The tree, the color, or something else? From human point of view, the word plate is a bit strange here. It could be motivated only by the pieces of the orange, and you might think that plate is there to show that you need a plate to offer these pieces. I don't know why plate is there, but this is one example. Here are the senses of the noun orange in WordNet. There are 5 noun senses. In the first one, the word fruit appears. In the second, third, fourth, fifth, no any word from the surrounding text to orange appears. And then is the adjective and the verb, but we worked only with nouns. What is the algorithm of LESC for words and disambiguation? We have an ambiguous word W in a text. We choose a window with suitable length around words around W. Let W has sense S in WordNet, and then for each sense we compute the number of intersecting words from the context and the gloss S in WordNet. Perhaps we can move this a bit. Yeah. And then we have a score, how many times words from the context and the gloss appear, how many words appear in the context and the gloss. And for each sense we compute this, we take the maximal score and say, this is the intending meaning, and the accuracy of this algorithm was between 50 and 70% when the algorithm was proposed, depending on the tag sense. If we go back to orange, we have for sense 1, the score is 1 word intersects. For the other senses 0, so the intending meaning is the first one, sense 1. Other examples. Shetland. And we have here the image with 4 tags, Shetland's collie dog. And in WordNet we have 2 senses, Shetland. First is geographical object, these are islands. And second sense of the noun, this is a kind of dog. We immediately see that the surrounding tags appear in the second sense. Okay, this is the meaning which is intended in this case. And please note that tags are a kind of abstract, they are a kind of text. So we have the same phenomena like with the text. When you talk about one object, you use the words from the gloss. So that's why we have this intersection here. Another object, another example. Water, spring, grass, rock. And we want to disambiguate the word spring. Spring has 3 senses in WordNet. One of the 4 conventional temperature seasons, elastic object used to store mechanical energy, any natural situation where water flows, and again we see immediately that the tags from the image appear in the glosses. We decide this is number 3, the sense 3. More complex example, we have this picture, this image, plate, salad, meat, tomato. What is the situation in WordNet? 3 senses of the noun. A plate is a broad vessel, tectonic plates, photographic plates. No of these tags appear in the definition of the glosses in WordNet. But if we take the definitions of the superconcept, the subconcepts, and the sibling, we'll see that the other tags, salad, meat, tomato, are food and what is certainly part of the definition in WordNet. So using this extended gloss search, we decide that the intended meaning is the first one in this case. And we were surprised that it is so simple and looked somehow very successful. It is simple, and again, we discovered that talking about something, even when you put tags, makes you use the words from the glosses. The algorithm works only for the words included in WordNet. And as I said, we worked only with the noun senses because we noticed that most tags that happen in general are nouns, and the automatic taggers that produce tags work with nouns. Another interesting object for disambiguation are the names, proper names, geographical locations, but we didn't address tags in this case. Let me show you the results after manual evaluation. We have 16 images. We worked with more, but the evaluation was done with 60 images from professional image marketplace into 3 categories: food, skin, children. There were many tags collected as additional information by the auto tagger of Imaga, and the accuracy was about 98%, which was even surprising. So food 20 images, skin 17, children 63 images. Number of tags, as you saw in the demonstration, Imaga delivers a lot of tags, core and additional. So we have 4,300 tags for these 60 images with different percentage of relevance. Most of them were words in WordNet. These are the tags which were outside of WordNet, less about 1%. Tags with one sense, 569, these are 13%. Most of the tags used for professional annotation had many senses in WordNet. And for a very high percentage of them, we received correct disambiguation. In image processing, when you classify it, you have such a category acceptable, not only yes or no, but such which is acceptable, and the wrong cases were only 157. So this was our first discovery that a simple algorithm for professional content-based annotation looks relatively well again, but we needed, how to say, we wanted to evaluate the approach using first much bigger collection, and second using the novel methods for words representation that appeared about 4 years ago. And we took another public collection of images, which was published in 2008, and tried to use this collection to evaluate to imagine some way to use it to evaluate our approach and to have a broader perspective from outside about how LESC algorithm can be involved in this task. MirFlicker is developed for content-based image retrieval. It's a rich resource for experiments in image processing, and it is prepared and published by one image processing community. So these are 25,000 images downloaded from Flickr through its public API. In Flickr, the images have manual tags, mostly in English. And in general, the data set contains 1,300 tags which occur at least 20 times in 20 images. The average number of tags per image is 8.9. And this collection includes the raw tags submitted by the user and also the cleaned tags, which are cleaned by Flickr, removed capitals, special symbol, etc. The annotators assigned manually categories to all images, and they were instructed to use a particular order of the tags, started from the wide sense to the narrow sense. And at first, what is tagged is the most general topic, but again, this is personal interpretation of the annotator. Let me give you one example of this image. So what you have in Mir Flickr, you have this very beautiful photo, and the tags, the categories assigned by the annotator are plant and water, and the tags which we have are dew, grass, wet, green, macro. I can't understand why macro appears here. Small, wee, blade, pointy, flicker, golf club, reflection, light, glassy, shiny. Another example, which I liked because of the female nature. The categories are female, people, plant life, and the raw tags are farmer in Indonesia. This is probably farmer, the lady which is harvesting rice. We have here four tags which point to the geographical region, Kisauk, Serpong, West Java, Indonesia. Then we have several tags which present the technical specification of the photo, Nikkor D300, and this is characteristic of the photo inside the collection, platinum photo, a big wave. So actually what we find in WordNet about this image, this is female, people, farmer, and Indonesia. So I want to show that in this collection, which is prepared for other purposes, you cannot rely to have only words as tags, but there are other things which are associated to every image. We worked with 5 categories: animal, food, people, plant life, sunset, about 19,000 images. Other 6 categories are sky, water, night, man-built structures, indoor, transport, but the first looked too abstract to us, too much, they contained too much landscape photos, and somehow we stopped here because 90,000 images looked sufficient number of data. We discovered that some 3,000 images had no tags, and we ended with 60,000 images, and every image has a category, sometimes 2 categories, more categories. So we had 20,000 image categories, pairs, and at tag level, we had 85,000 tag category pairs. Our assumption how to test the correctness and the feasibility of the LESC algorithm was the following one. First, you have no gold standard in image annotation. There are no such data sets, and we didn't find anyone. So we somehow did something manual, but later there was no gold standard. And as external resources, we again used WordNet because it is more classical and accessible. There are many other things associated to a tag, to a word. You have there the lemmas, the glosses, the synonyms. So WordNet brings additional information to these words. And our assumption was the following: if our tax and disambiguation is successful, Then the word embeddings calculated using the wordnet feature lemma. For the bridge, and our algorithm with the less checks suggests the following sense: something resembling a bridge in form or function. That this is the meaning of the bridge in this case. So we calculate the embeddings. If we calculate the embedding between bridge and plant life, this is one word, it has its embedding, and this is the category. Two words, again, we can calculate the embedding. The similarity is 32%. If we calculate the mean lemmatized gloss embedding between something resembling bridge from bridge in form or function, but the stop words are removed, and bridge, and then we have plant life, then the similarity between the gloss and the category is raised to 76%. In our interpretation was, if closeness increases, then the taxon disambiguation is correct, especially for this tag and for this image, for this context. This was our assumption. And what we did in this larger scenario, we used 300-dimensional vectors in 3 models. At that time, 2018, what was popular, these were the Google embeddings, 3 million words and phrase vectors trained on news, on a large corpus of news. This model was known to be generic because it is trained on news, on separate word forms without lemmatization. Then we used a model trained on WordNet, provides representation only for lemmas and only for open class words, nouns, verbs, adjective, and adverbs. And then we had in our group model 3, extending model 2, a Wikipedia dump was lemmatized and concatenated to this pseudocorpus used in model 2. So for us, this turned to be the best model where Wikipedia was used as a training resource. Certainly I talk about the English Wikipedia. And we calculated a lot of things, a lot of embedding scenarios. At first, we worked on image category pairs, and for every image we calculated. Let me only briefly here summarize the mean vector of the word embeddings of the raw tags, the mean vector of the word embeddings of the words in the tag glosses obtained after taxon disambiguation with stop words removed, the mean word embeddings of the raw tags and their synonyms. We added synonyms, the word phrase embeddings of the image category. Other setting of the experiments with models 2 and model 3, we calculated similar things. For the lemmatized raw tags, this proved to be the best one. with stop words removed, adding synonyms, all synonyms in lemmatized forms. Synsets also had their raw tags only for Model 3. The word phrase embeddings of the image category. Another example for the experiment for the tag category pairs. Lemma embedding for the tags, the lemmatized words of the tag gloss with the tag lemma. I don't want to read them all because I don't believe you, how to say, remember all these things that was done. And then we compared the vectors as I showed. For every experiment, we can compare the vectors to the category vector to see which is the closer one. And to summarize the results, in general, we made two types of comparisons. Between the raw tag set embeddings to the category embeddings and between the embeddings of the enriched tag set with WordNet features, which means adding lemmas, glosses, especially synonyms to the category embeddings. And we also did manual check for some images, 100, 180 per category. The accuracy was for food 87%, sunset 86, animals 85, people less, plant life 67, botanic terms were wrongly disambiguated. Best results were achieved for Model 3, and it turned out that the gloss embeddings improves the results in 88% of the cases, and for Model 2 and 93% of the cases by applying Model 3. Do the synonyms increase the semantic similarity? Yes, partly, 50 cases, 50% of the cases, 53% of the cases. And only for Model 3, we had a better result that synonyms help to enrich the informations. And glosses and the synonyms seem to contribute equally to the tag category semantic similarity. So the conclusion is that the more words, the more context you involve in the computation, the better your disambiguation becomes. There were many errors in this disambiguation process, and we discovered many things about the tags, which we didn't know because we couldn't check them manually. There were too many, 20,000, 30,000 tags. Often error, assigning a word that says, which is a verb. This can be fixed if we introduce lower weights to the verb senses. Simply the words in the glosses of the verbs make this sense to appear as most probable one. Names of locations are often erroneously resolved to personal names. Mirflicker contains many names, as you saw, geographic locations, and the data-specific error. Among the raw image tags, there are camera metadata, such as camera model and photograph settings, and these were wrongly assigned to WordNet meanings. What can we do more? Actually, our idea was to segment videos to images, to take the tags which are assigned automatically, and to try to work with video meaning or something to aggregate these separate tags. But it wasn't a good idea to approach the issue in this way. The next that we can try, especially for tags, is to involve the word sense embeddings, which appeared recently, because 2 years ago we had embeddings on word level, and now we have many more sets of data sets of embeddings, Some of them are trained for senses, so we can start with this with these sets, data sets. And I think it is very inspiring to nowadays to think that taking an image and its tags, you are able to identify the sense behind the tags. But as I said, the issue is difficult, and we made only a first step in understanding how to approach this issue. We can try with Wikipedia and sense-based embeddings. Probably it would be very helpful if we can observe better the output vectors to know where they in the space and to look what happens with the vectors we calculate, because now we see them only as vectors. What we didn't do is to reflect the order of the tags. We know that they are assigned from the more general to the more specific meanings. So to do something with this order of the tags, and certainly to work with the named entities in the tags. The first lady here, both of them smiles. The first is Olga Konishcheva from Kharkov. She was our postdoc for more than a year in the Akumin project. The second one is Evelina Nikolova, a member of our group. They have two sons during the last 2 years. I believe that both of them had a baby 2 years ago, so I believe that now we can continue with the work when the kids grow up, and to help to involve the new data sets and new types of embeddings that appeared recently. Thanks for your attention. Any questions? Here? I was wondering whether you consider WordNet The first question, you know, there are image sites which are organized 10 years ago using WordNet, and the Tagger Fimaga uses 3,000, used at the time 3,000 patterns associated to the meanings of WordNet. So when this process of collecting tags images started, the first big sites were oriented to WordNet and the senses. This happened 10 years ago. Certainly today the situation is different. There are more resources, and it is worth trying. Concerning the second question, yes, you have many words appearing at different places. What I present here about the decision making with the Lesk algorithm is a bit simplified, because we didn't discuss any details, but these are the results, 98%. Yes, there are scores with similar words, but we take the first one, and this is the correctness, yeah. Sure. That's why in the second case, when you used with the embeddings, senses associated to verbs appeared, because of the similar words that are verbs and appear in the gloss of the verb. instead of the verb with the noun. But this, we found it in the embedding. Yeah, not in the first case, which we checked manually there. Because we reduced the verbs when we work manually, only with nouns, but with the embedding, the situation is different.
First of all, I would like to thank Prof for inspiring. And that is one question. What sense is the word that
No.
because you mentioned that there are different results, for example, for education, for food, for persons.
Something else, because actually we come from artificial intelligence, and we looked at this main task, integrating vision and language. So our idea was somehow vaguely, you have the image primitives, because at the time we worked with Imaga, from an image classifier. They tell us what a classifier can do. It gives you words with relevance. And if we take this image annotated in this way, and these are the primitives found in the image. And now we continue with language processing to understand what is there, really. Yeah, and this was our work done so far. But it very much depends on the pattern. What you say, it always depends on the pattern, because if you see now with the Imaga Tiger, his breech was not good, the lung was not good. It simply depends on the pattern. But the surgeon, the people with operations and masks, this was good. There is such a training pattern that helps you classify these types of images well. Certainly, they are very good with food because they want very much in the restaurants to have online systems where you make a photo of your plate and send it to a platform, and it tells you what you eat, and it could be helpful in tourism when you want to select your food or something. And this is important when you do shopping in the supermarket to know what is what. For example, food is very typical domain for image processing in such, how say, industrial settings and online social sites, or you share what you eat with your all the world. You immediately post in Facebook what is in your plate. This is important. Food is certainly, but concerning the others, I somehow see no difference. There is one difference, whether this is manual annotation for subjective reasons in your personal collection, or whether this is professional. This is when you discuss the objects that are seen in the picture. If there are no questions, once again, the last slide, thank you for your attention. At the end of the presentation, I am already specialist in this video projecting system, so I know how to do it. Thanks for your attention once again.